So today we're going to talk about something called conservative and non-conservative forces. And these are going to have to deal with the amount of work that's been done, the amount of energy that's been expended. We're looking at these two different types of forces. Okay, so conservative forces are forces for which the work does not depend on the path that's taken to get there. Which means we're really looking at only the starting point and the ending point. Okay, we're not really concerned about the path that it's taken to get there. We're only concerned about where it starts and where it ends. Okay, so things like gravity, things like forces in a spring to begin and end as a spring is stretched or compressed. Those are types of conservative forces. So we don't care about things that happen in the middle. We only care about the starting point and the ending point. Okay, opposite of that is something called non-conservative forces, and these are things are types of forces for which the amount of work does depend on the path that it takes. So you can do more work depending on the path that you take to get to your final destination, or you could do less work. Okay, things like friction, air resistance, tension, an applied force, all those are non-conservative forces because it does depend on the path that you take. Okay, if we're looking at the amount of work done by friction, it depends on how much our particular, or how long our particular force is applied, how much distance is covered while applying that force, right? Because work is equal to force times displacement. Okay, so it does matter the path that we take to get there. So these are two different types of forces, and it's going to make a difference because we're looking at the amount of work that can be done and the amount of energy that's transformed. Okay, so when we're talking about potential energy, we're only going to be looking at conservative forces. Okay, so when something has potential energy, we're only looking at the starting and the ending points. We don't care about the path that it took to get there. We're only looking at the potential energy at its starting point and at its ending point, or at some point in between, right, where we make a new starting and an ending point. Okay, so that's only going to be for conservative forces. So now we're going to be able to include potential energy into our work energy principle. Okay, the original work energy principle that we looked at told us that work was equal to change in kinetic energy. Okay, now we're taking it a step further and we're talking about non-conservative forces. Work done by non-conservative forces is equal to the change in potential energy plus the change in kinetic energy. Okay, so work that's done by non-conservative forces acting on an object is equal to the total change in kinetic and potential energy. Okay, so even though potential energy can only be defined for a conservative force, we can still go ahead and plug it into this equation for non-conservative forces. Okay, and you can follow through this whole derivation of how that works to get the math to put it into the work energy principle. That whole derivation is on page 158 in your textbook, and if it helps you to read page 157 and 158 about this connection between conservative forces and non-conservative forces, and how potential energy works into that, you can. It's on page 157 and 158, and it might be a good idea if you want to go ahead and read that. Okay, just to review, when we're talking about work done by non-conservative forces, we're talking about things like friction, tension, air resistance, anything that's applied. Those things are path specific, so we do care about the specific path that they take. Okay, so even though potential energy is always associated with a force, a conservative force to be exact, not all forces have a potential energy. So friction does not have a potential energy because there's no potential resting in friction. Okay, so our change in potential energy there might be zero. So now on the other side of that, what if we only have conservative forces that are? So what if we only have conservative forces acting? We've got work done by conservative forces, W sub C, is equal to the change in kinetic energy plus the change in potential energy. Okay, if only conservative forces are acting, our work is going to be equal to zero. Okay, which means that kinetic energy plus potential energy of conservative forces is going to be equal to zero. Okay, and examples of these are gravity, things that are elastic like springs. These are things where we're not concerned about the path. We're looking at the end and the beginning, okay, or the final and the initial positions. And I know this seems all just a little bit foreign and a little bit abstract, but we're going to connect this work energy principle into something specific called mechanical energy, and that's going to be able to look at the energy of the whole system. So we are working towards something, but it is, I understand, a little bit abstract for right now. Okay, so if we're looking at the total mechanical energy, which is the sum of the potential and kinetic energy of a system, whether it's conservative or non-conservative forces acting, we're not really concerned with that conservative or non-conservative once we get past that work portion. Okay, so now we're really looking at this mechanical energy, which is the total energy of a system at any point in time. Okay, so the non-conservative and conservative forces portion really only goes with the work portion of it, and we're not going to cover much of that in this chapter as far as work done by conservative and non-conservative forces. It was kind of a relay to get to this mechanical energy section, which is separate from work. Okay. So mechanical energy, which is going to be identified with a capital E. So this capital E is going to be our variable for mechanical energy, or total energy of a system. Okay, at any point in time, the energy of a system is going to be equal to its kinetic plus its potential energy. Okay, again, it might have both of these types of energy. It might only have one, depending on its position or its location and its path. Okay. We can combine the energies to form one equation for the conservation of mechanical energy, which means that mechanical energy before is equal to mechanical energy after. Kinetic energy after plus potential energy after is equal to, it's going to equal the kinetic energy before plus the potential energy before. I'm not really sure why I would have put the after on the left-hand side and the before on the right-hand side. That does not mean anything at all. It's just probably how it was written in the book, but we're really usually going to put the initial on the left and the final on the right. So if it makes you more comfortable to rewrite this as 1 and 1 and 2 and 2, so you know this is before and this is after. So this might be at a certain point in time before and a certain point in time after, or initial and final, or however you want to think of it, but essentially we're going to look at the energy before is going to equal the energy after some big movement or some action that happened, okay? But this is the conservation of mechanical energy, which means no energy has been lost or created throughout this action. All right, so I just showed you the equation for the principle of conservation of mechanical energy, but here's kind of a word description, and this is where we get a connection to our conservative and non-conservative forces, again, from that previous section. So this tells us if only conservative forces are acting, things like gravity, that means the total mechanical energy of a system neither increases nor decreases in any process. It stays constant or is conserved. So you do need to have this paragraph down in your notes. This is just telling us that for things in which we don't care about the path, right? Conservative forces like gravity, we have a conservation of mechanical energy. So we've looked at this equation for mechanical energy. Energy equals kinetic plus potential. Now we're going to substitute the equation for kinetic energy and the equation for potential energy into that equation. Okay, so this tells us at any point along the path, total mechanical energy of an object moving with conservative forces can be found using this equation. So this is essentially one side of our equation, okay, because we had E1 equal to E2. So this whole portion right here is essentially one side of our larger equation. This tells us at any one point in time. So this is looking at one still frame of an energy, of an object in motion. We're looking at energy at one point in time. Here in this particular equation, we're not looking at the before and the after. We're looking at one specific point in time. Okay, so this is 1/2 of our equation essentially, or if we want to find it just at one point in time, we'd use this equation. If we want to look at two a before and an after, or at 2 points in time, or whatever, we would use this larger equation. Okay. You can calculate mechanical energy at 2 points along any path using this equation. So this is where we said, again, energy initial is equal to energy final. And then we plug all of these in. And I went ahead and switched it again here to make sure that we see that initial usually goes on the left with the ones, and final goes on the right. Okay, I'm not, again, sure why I have the 2's and the 1's mixed up here, but if it makes you feel better to switch those, go ahead and do that. Okay, so all I'm doing is changing the subscripts so that you see initial always goes on the left, final always goes on the right. Okay, but this allows us to calculate these things at any 2 points, so before or after or initial and final, or however you want to think about it. Okay. So I'm going to clear this off. It's important to remember that this would be a velocity, right? V is equal to velocity or speed at that point. Y is going to be equal to the height of the object off the ground. Okay, remember we use that equation solving for potential energy. So here's kinetic energy, potential, kinetic, and potential. Okay? So let's go ahead and start looking at some problems here. Okay, just before an object hits the ground, all of its potential energy will have been transformed into kinetic energy. So as I look at an object that's falling through the air, okay, so if I start an object up top and it starts to fall through the air, at the top, at the very, very peak, it's got all potential energy. As it starts to fall, we make a switch from potential to kinetic. Might be about half and half, might not be about half and half. We could do calculations to find it. As we fall a little bit further, we made an even bigger shift to kinetic energy. It's even closer to purely kinetic. And then as we reach the bottom of our path, we've made a transition to having only kinetic energy. At the very bottom of its path, it has no more potential. Okay? It cannot fall any further, which means it has no more potential energy. So by the time it reaches the bottom of its path, it's been transformed all to kinetic energy. Okay, so here at the top of its path, we begin with all potential. At the bottom of its path, we then have all kinetic. All right, so go ahead and, if you need to pause the video to get this written down, go ahead. But we're going to start looking at our object here. Okay, so we've got a stone that's at a height of 3 meters. It's going to fall until it's a distance of 1 meter above the ground. Okay, so here's the ground right here. It starts at a height of 3 meters and it's going to fall until it's a distance of 1 meter above the ground. Okay, so let's think about this at the top of its path. We've got all potential energy. At this point on its path, it hasn't completely fallen all the way to the ground, which means it's going to have both kinetic and potential. We have not made a complete shift to being fully kinetic energy. We have both of those still present. We've got still some potential because it can still keep falling, but some of that potential energy has been transferred to kinetic energy. So we've got both. Okay, so this is initial and this is final. Okay, so let's go ahead and set up our equation here. We're going to say E1 is equal to E2. Then we can go ahead and start our equations. Kinetic energy initial plus potential energy initial is equal to kinetic energy final plus potential energy final. And then I'll go ahead and start making my substitutions. So I'm going to say, I know it has no kinetic energy at the beginning, so I'm just going to go ahead and plug in a 0 there. I know the equation for potential energy is mgy. The equation for kinetic energy is 1/2 mv squared plus mgy. Okay, so again, this whole left side of my equation is my initial, my starting point. The whole right side of my equation is the final. So I don't know the mass of my object, so I'm just going to keep it as an m for right now. Our gravity we get to plug in is positive 9.8. And our y value tells us our height off the ground, which is 3 meters. Okay. 1/2, we still don't know our m. And we're solving for velocity, so we're going to keep that as v squared. We don't know our m, we're going to take it times 9.8 and times our final height, which is 1 meter. Okay, so the whole left side of the equation should be 9.8 times 3, so 29.4 m equals 1/2 mv squared plus 9.8 m. I want to combine those like terms, so I'm going to subtract my 9.8 m over. Which gives me 19.6 m equals 1/2 mv squared. Okay, I can go ahead and divide by 1/2 m. Divide by 1/2 m, and I cancel my m's at that point. I'm going to have to give myself some more room, so I'm going to go over here to the left. If I divide 19.6 by 1/2, I get 39.2 equals v squared. I want to square root that answer, and I get a velocity equal to 6.26 meters per second. Okay, and our velocity is in the downward direction, which means we need to include that negative. Okay, it's going in the downward direction because our stone is falling. So in this problem, it's really, really important that you understand we begin with all potential energy, but at the bottom, or our final, the second portion of our problem has not reached the bottom of its path. Okay, it has not reached the bottom of its path, so not all of that energy has been transformed to kinetic energy. If it would have fallen all the way to the ground, we would have only kinetic, but it didn't. It fell to 1 meter, so we've got kinetic plus potential. That's really important for you to see, otherwise our velocity would have been way off. All right, on our next one, go ahead and pause and get written down if you need to. All right, let's see what our roller coaster looks like here. We're going to start up at 40 meters, and we're going to travel to the bottom. Okay, so we've got a height difference here of 40 meters. We'll start right up here, and we're going to end 40 meters below where we started. Okay. So this is the height of the top hill of the roller coaster. That means we've reached our absolute peak, which means at the top we have only what type of energy? We have all potential at the top. Once we've made our way down the roller coaster to the very bottom, we've transformed to all kinetic energy. Okay, so this is initial, and this is final. So we can go ahead and start plugging in our variables here to our conservation of energy equation, which is 1/2 mv squared plus mgy equals 1/2 mv squared plus mgy. Okay, at the beginning we said we have all potential, so we don't need that kinetic energy equation, and at the end we said we had all kinetic, so we don't need this potential energy equation. Okay, now we're going to take m times 9.8 times our y value, which was 40. We're going to set it equal to 1/2 m times v squared. Again, our m's are going to cancel here, so we don't really need to know the mass, but this is 392 m equals 1/2 mv squared. So we'll divide by 1/2 m, divide by 1/2 m. That's going to cancel our m values, and going to give us 784 equals v squared. And it's going to give us a final velocity of 28 meters per second. Okay, this object is not falling in the downward direction. We're kind of just going to consider this roller coaster path to be the positive direction, so we can keep that at a positive 28 meters per second. Okay, so we found that the answer at the bottom, okay, at the completely bottom of the path, is going to be equal to 28 meters per second. Now we want to find out what height will the car have half of this speed. Okay, so let's look at our roller coaster again. At the top, we've got all potential energy. At the bottom, we have all kinetic. And we know here it's traveling 28 meters per second. So we want to find where along this path does it reach a speed of 1/2 of 28. Okay? It doesn't change the fact that our car starts at the top of the hill, which is 40 meters above. So we still have only potential energy at the beginning. Okay? So we're still going to say 0 plus mgy is equal to. And now for the second placement, we don't know where along this path it's going to reach a velocity of 14 meters per second. Okay, the 14 comes from the 28 divided by 2. We want to know when it reaches half of that velocity. Now, it might be easy to think, oh, it's going to reach it right at 20 meters because that's half of its height, which would mean it's going to have half of its speed. That's not the case. Okay, that's not the case. And it's not the case because we've got an acceleration equal to 9.8 meters per second per second. So with every second, we're increasing our speed by 9.8 meters per second. So it's not just a direct correlation there. So we can't just assume that it's going to be 20 meters. We're going to find at what point along this path does it finally reach a speed of 14 meters per second. So we're not at the top, we're not at the bottom, which means we're going to need to have both kinetic energy and potential energy. Okay? And since we're solving for height, at what height? We're going to solve for a y value. We're going to solve for this variable right here. Okay? Again, our masses are going to cancel out, so I'm going to go ahead and just cancel those ahead of time. It's the same vehicle the whole time. We don't need to have that mass in there, so I'm just going to cancel those. Okay, so we're going to take 9.8 times 40 equals 1/2 times 14 squared plus 9.8 times y. Okay, again, the 14 comes from, the question asks us at what height will it have half of that maximum speed. Okay, so we get our y value equal to 30 meters above the ground. 30 meters off the ground. So it leaves at 40 meters. 40 meters above. Once it gets to maybe 30 meters above the ground, it's reached that 14 meters per second velocity. Okay, it wasn't half. It was before it reached the halfway point. So it got there pretty quickly. So it's important for us to understand that although it's half the speed, it does not necessarily mean it's half the height. Okay? And again, the reason we use both kinetic and potential here is because we knew it was going to be at some point on this curve, on our roller coaster path. It wasn't going to be at the very bottom, wasn't going to be at the very top, so it's got to have both types of energy in there. Okay, let's go ahead and take a look at this problem. So pause it if you need to get it written down. For this example, we're looking at spring potential energy now instead of gravitational potential energy. Okay, this is again a conservative force, so we can use our equation here for springs and for gravity type of problems. Okay, so here we've got this dart with a mass of 0.1 kilograms. It's pressed against the spring. The spring is compressed to 6 centimeters. If the dart detaches from the spring when it reaches its normal length, what speed does the dart acquire? So it means we're solving for velocity. Okay, we know mass is equal to 0.1. We know that our spring constant is equal to 250. And we know our compression, or our x value, is compressed 6 centimeters. First of all, we need to convert that to meters. Okay, and since it's compressed, not stretched, we have to include that negative. So as we think about this dart gun and we think about what it's looking like, we've got a compression to begin with and a complete release of that spring to end with. Okay, it's reached its final point. Okay, that means to begin, we have all potential energy to begin with. So all potential energy at the beginning. When it's released, it's all been transformed into kinetic energy. Okay, we're not at some halfway point on the spring. We're at full compression of that 6 centimeters, and we're at complete relaxation or release of that spring. So we're going to transfer all that potential energy into all kinetic. If we were to look at the spring somewhere between those 2 points, let's say at 3 centimeters, then we would have a mixture of potential and kinetic as our final energy source. But since it's been completely back to normal, x equals 0, that means we've transferred all that potential energy to kinetic. Okay, so that means initially we're going to have kinetic plus potential equals kinetic plus potential. Okay, something that we want to think about here is this is not gravitational potential energy. So we have no kinetic energy at the beginning, but we've got spring potential energy, and there's a different equation for that. So you need to take a look back into your notes to find the potential energy equation for a spring, because it's different. Okay, and hopefully you found that equation, and it's equal to 1/2 kx squared. Okay, at the end we determined we have all kinetic energy and no potential energy. Okay, it's all been transformed. So we're going to go ahead and plug in here 1/2 times our spring constant, which is k, times x squared. Is equal to 1/2 times our mass, and we're solving for velocity. Okay, so let's go ahead and look at the math here. The whole left side gives us a 0.45. We have 0.05 over here times v squared. So 0.45 divided by that gives us 9 equals v squared. So that means the velocity that it reaches is 3 meters per second. Okay, so as this dart is released from that spring and released from the gun, it reaches a velocity as it exits the barrel of the gun at a speed of 3 meters per second. And that's going to be where we stop today with mechanical energy. So, and I have some problems to do.